Right, good morning to you all and welcome back. I shall be waiting here for like 5 more minutes since not many people has joined. So I would expect more people to join and then we shall start. So if please let me know if the audio and video quality are fine. So please let me know if the audio quality is fine, especially. All right. So let's talk about what we are going to talk about today. So first of all, we are going to have a recap on the flag register. See, you might recall from our last class that the flag register in combination with the accumulator is also known as the program status word PSW register pair, right? Accumulator and the flag register combined is known as the program status word register PSW register, right? So you might already recall that, right? So I already told you why is it called a program status register, because after executing a program it is very likely that the result will probably be stored in the accumulator. Okay, and after that the status of executing a certain instruction, if you execute an instruction, the status of that, okay, and what I mean by status you shall soon understand, is stored in the flag register. So flag register often is used to figure out what was the status of the last executed instruction. Okay, so there is one question here. Yeah, if you one question just arised from our last discussion. Someone is asking that what if we do move a comma h instead of doing move a comma m? What will happen is, for example, before that I did, for example, lxi h comma 3456, right, something like that. All right, so my h register had a value of 3 4, so I am answering a question one of you raised, and L register had a value of 5 6. I was using the HL register pair to point to the memory location 3456, so that through the fictitious M register we could bring up that data which is stored in the memory location 3456. All right, but if I just do this, what will happen? Just the content of H register will be copied over to accumulator. So after doing that, the accumulator will now have 3 4, but that wasn't our intention, right? All right, so I think I answered your question. So if I just do that, the content of H register will be copied over here, right? The content of H register will be copied over. And what is the content of H register? Of course 3 4, right? So it does not solve our objective that we had in our earlier class. Our objective was to store the data in a separate memory block, so that we can just change the data and we won't have to change the program itself to execute the program on different set of numbers. So there is another question. So let's say can only yes, problem is it's not a question of which which instruction can access which register, right? So for example, okay, I might as well have done something like this. For example, I could have done LXI B comma 3 4 5 6. I could have done that. I could have done that. I could have done LXI B comma 3 4 5 6. In that case, B register would have gotten this and C register would have gotten this. Alright? Alright? But there would not have been any memory pointer to talk about in that particular situation, right? So what is the memory pointer? Memory pointer is a fictitious register which points to the data that is stored in the memory location pointed by the HL register pair. Now under this scenario, if I do LXI B comma this, and then what happens? B and C, these register pair gets a value, right? These would get these two values, right? But we wouldn't have the memory pointer to talk about. But when we do something like this, we now have two things that we can do. Rather three things we can do. Okay, we can treat the H and L registers individually and do whatever we want with their data. One thing. The second thing is that we can use HL register pair as a 16-bit register and we can do 16-bit operations on that. Okay, we can treat this as a 16-bit register, 16-bit general purpose register, and manipulate its data. Okay, right? So that's the second thing we can do. Or the third thing we could do was use the value that is being stored that. So HL has a value of. HL had a value of 3, 4, 5, 6. So, or we could use it for the third purpose. What was the memory pointer, right? For example, HL had a value of 3, 4, 5, 6. Again, I'm telling you, the first use would have been probably could have been the case where we would use the H register and L register individually. Okay, so we would probably have done some operation on that. So some kind of mathematical manipulation or anything we could have done on that. So we could have used them as separate 8-bit registers. The second purpose we could have used this HL register pair for as a 16-bit register pair. So this would have been a 16-bit data. Okay, we could have done 16-bit operations on that. We shall soon see operations like that where we would treat this not as a memory pointer but just as a 16-bit register to do 16-bit operations on. Okay, so we could have done that. Or the third objective was to use this as a memory pointer, and under that scenario we could have treated this as a memory pointer, and what we could have done was take this, give HL register pair some value, and whatever value it gets is treated by the memory address by the memory pointer, for example. Okay, so if this has 3, 4, 5, 6 in it, the HL register pair, then this fictitious register, which is also known as the memory pointer, would be pointing to the content of that particular memory address. For example, this memory address is 3, 4, 5, 6. Whatever data I have in this register, okay, whatever data I have, so maybe I have a data, say for example 70, maybe 78, something like that. That data will be pointed by register M. Okay, so that is how we can sequentially pull and put data into the register, into the memory, right? So that is something we can actually do. Again, feel free to let me know if you have any query. All right. So with that said, let's clear these things up. So again, if you have any query, feel free to ask. So quite a few people have joined. So let's start our discussion today, right? So the first thing we need to discuss is this status register, also known as the flag register, right? So the flag register, of course, has 8 bits in it. Okay, and I shall show you what the flag register is by means of doing a few operations, and then we shall jump into jump instructions. We shall talk about jump instructions later on. And again, during the class, if you have any query regarding anything, feel free to ask. I shall be answering all of your questions. So with that said, let's jump into our flag registers. All right. So here you can see the flag register is there. So this is the flag register. Okay, we get to see the flag register. Now try to understand that this flag register is accessible by you as a programmer and also by several other instructions known namely the conditional instructions. So there are instructions that check for a condition based on the status of the flag register, and based on that, whether the condition is true or false, based on that something will happen or maybe something will not happen. Okay, so we shall see that. So right now look at the flag register. Now of course every single register, 8-bit register, has of course 8 bits. Now in the flag register of 8085 microprocessor, I have 5 bits that are reserved for different kinds of flags. Okay, and then we have 3 bits that are reserved for future use, but these weren't used at all. So we have a flag register where only 5 out of 8 bits are actually used by the microprocessor to do something important here, something anything here in fact. Okay, so whenever you are doing something conditional, okay, whenever we are checking for a condition, those conditions are checked through the flag register. Now what is this flag register? So there are a few things in the flag register so that you need to remember. So this is the flag register. So hold on. And again, if you have any query, feel free to ask. So let's start with the flag register. Okay, so of course any register is an 8-bit register. All right, so we have the sign flag, the zero flag. Okay, then we have a reserved case. Okay, then we have an auxiliary carry flag, then we also have a reserved case once again, then we have a parity flag, and then we have the carry flag. All right, so these are the flag registers, individual flag registers present in the 8085 microprocessor. Now we shall discuss every single one of them individually, but let's look at the most important flag, namely the carry flag. Okay, so what is the carry flag? So of course you understand what the carry flag means, or is rather. Okay, so the carry flag indicates whether the last operation that you did or last instruction that you executed resulted into a carry or not. Okay, if the last instruction that you executed resulted into a carry, then the carry flag will be set. And when I say a flag is set, it means the flag has gotten a value of 1. So if I say, so this is the flag register and these individual bits are the flags. Okay, this is the flag register. The flag register contains all the flags. Okay, and these individual bits are the flags. Now out of these, this bit and this one, they are not being used. Okay, and only these 5 are used, right? So now of course these individual bits are here the flags, for example. So when I say a flag has been set, it means the value of the flag has become 1, right? So setting a flag means setting a flag All right, I think we are back online. So it's really becoming a headache. Okay, the internet connection is really becoming a headache lately. All right, so I shall resume. Anyway, all right, all right. So thanks for patiently waiting. So let's resume our discussion here, and I hope it won't break down once again. So the Alliance people are somehow restarting their server every single day whenever I'm doing my classes here. They just happen to restart their servers. That's it. All right, setting a flag means that we are something happened so that its value has become equal to 1, and I have to reduce the gain of the mic. All right, that's understood, right? So there are now 5 flags of importance here. Out of this, the carry flag is most important. Okay, so what does the carry flag happen to do? This carry flag indicates whether the result of the previous operation or result of the previous instruction gave you resulted into an overflow, so that is a carry, or a borrow. So if after doing an arithmetic or logical operation, mostly an arithmetic operation, if there is a carry or a borrow, in that case the carry flag is set. Okay, so this is known as a carry flag, but it indicates so if this is still loading, please refresh your please refresh your YouTube. All right, this is becoming really annoying. So this is the carry flag. Often carry and borrow flag. Okay, so this flag indicates whether there is a carry or there is a borrow. There has been a borrow in the last executed instruction. Okay, after the last executed instruction, whether there was a carry or not. Okay, if there was a carry, the carry flag will be set. Now what about the auxiliary carry? Auxiliary carry and auxiliary borrow is the same. Okay, and it indicates whether there has been a carry or a borrow from the 3rd bit into the 4th bit. What I mean, okay, example, let's take an example like this one. Say we are adding 2 hexadecimal numbers. Okay, let's add 2 hexadecimal numbers and see how we actually proceed from that, how we understand that. Okay, so let's add 2 hexadecimal numbers, maybe for example 9b. So that's one number. We're adding that with okay, we're adding these 2 numbers. Of course, let's do it the binary way. Okay, let's do it the binary way. So what is the equivalent binary of this? That's 1 0 0 1. And what is the equivalent of b? Of course, b is 11, you can understand. Excuse me. Of course, b is 11, so that's that much. All right, all right, so we have these. And what about 7? That's okay. And what about 8? That's 9. Now we are adding these 2 numbers. Let's do it the binary way. Okay, and if we are adding these 2 numbers, let me just segregate these in a slightly useful manner. Let's segregate these in a slightly useful manner. Let's give this a different ink. Okay, so 1 plus 0, that gives you 1. 1 plus 0, that again gives you 1. This 0 plus 0, that gives you 0. This 1 plus 1, what does it give you? 1 plus 1 is equal to 1 0, right? So 0 remains and 1 is carried over to the higher nibble here. So in one byte you have 2 nibbles. One nibble is a hexadecimal digit. A single hexadecimal digit would take up 4 binary digits, right? A single hexadecimal digit would take up 4 binary digits, and this is one set of 4 binary digits, this is one set of 4 binary digits, right? So now here 1 plus 1 has a sum of 0 but has a carry of 1, and that carry is forwarded to, that carry is actually forwarded to this one. Get the point, right? That carry is actually forwarded to this. So whenever there is a carry that's forwarded from the lower order nibble into the higher order nibble, so this is the 0th bit, this is the first bit, this is the second, third, this is the fourth, this is fifth, this is sixth, seventh. Okay, so whenever there is a carry from the third bit into the fourth bit, okay, so from the lower order nibble into the higher order nibble, and while doing 8-bit addition, then it's called an auxiliary carry. So if I add these two numbers, then the auxiliary carry flag would have been set. Okay, so the value of the auxiliary carry flag would have become 1 to indicate that there has been a carry, okay, from D3 to D4. It's often written as D3 and D4, digit 3, digit 4, understandable, right? So from this to this, if there is a carry, then it indicates that there is an auxiliary carry. This is known as an auxiliary carry. Okay, let's carry on the calculation. So I have an auxiliary carry 1, so I have 1, 1 and 1. The addition is 1, 1. So I have 1 here, I am carrying 1. So 1 and 1, okay, 1 here and carry 1. So addition is 0. I also have a carry 1. So 1 and 1, right? 1 and 1. So again 0, I am carrying 1. Again 1 and 1, so addition is 0. Now I have yet another carry which is 1. Right? So after doing this addition, so if with using the microprocessor, if I add these two numbers, not only the carry flag will be set, the auxiliary carry flag will be set. Because of this, the auxiliary carry flag will be equal to 1. So the auxiliary carry flag will be set, but also the carry flag will also be set. Okay, carry flag will also be set, indicating that there has been a carry. So the auxiliary carry flag will be set, indicating that there has been an auxiliary carry, but also the carry flag will also be set, indicating that there has been a carry, right? So, and everything like all of these will be indicated in the flag register itself. Okay, all of this will be indicated in the flag register. Okay, so you get the point. I get the point. Of course, after doing the addition, the result of the addition would simply be 1 as a carry, and this is hexadecimal 1. Again, here I am writing the hexadecimal numbers, and this is in hexadecimal 13. So the sum would be 13, carry would be 1. Okay, and inside that there would also be an auxiliary carry. So again, if you did not understand the idea of auxiliary carry, please let me know. Of course, you understand the idea of carry. And again, while doing subtraction, for the most significant bit, if you have a borrow, in that case, the result will be result will give you an carry flag. Result will also set a carry flag. Set the carry flag. So carry flag indicates both carry and borrow. Okay. So if the most significant bit, addition or subtraction, results into a carry or a borrow, then the carry flag is set. Similarly, this one is known as an auxiliary carry. Auxiliary carry flag. So this is an auxiliary. This is the auxiliary carry flag, and of course we talked about the auxiliary carry. But feel free to ask if you have any query regarding any of the discussions we just made. Again, I would believe that this is quite simple to understand, right? Okay. Again, now let's talk about the third most important flag. I mean, the auxiliary carry isn't that important, really isn't that important. I haven't, for myself, I haven't really found any good use of the auxiliary carry flag. My experience might be limited, but yes, this does not have as many uses as the other ones. Okay, so this is known as the zero flag. Okay, what happens when what are the conditions under which the zero flag would be set? The zero flag would be set if the result of an arithmetic or logical operation is 0. Okay, so you executed an arithmetic instruction or a logical instruction and the result was 0. Okay, then the zero flag would be set. So let me give you a few examples. So examples where the zero flag would be set. Let's see a few examples where the zero flag would be set. Okay, a prominent example would be something like this. Say for example, I did something like this: MVI A, comma, say for example 57. So in A register I have 57 stored. Okay, say I have MVI B, comma 57. So both of them have the same number stored, right? So if I do something like this, sub B. So this is an instruction, and obviously by the name of it you can understand what it does. It subtracts subtracts the content of register B from that of register A and stores the result into register A. Okay, this instruction subtracts the content of register B from register A and stores the result into register A. That is what sub B does. Now, of course, since both the numbers are identical here, what would happen? The result would be a 0. So in the accumulator I would have a 0 0, right? And whenever something like that happens, the zero flag is set. So this example would set the zero flag. Okay, I'm not thinking about the other flags. Other flags probably will be affected as well. Okay, but I'm not talking about those right now. Okay, I'm just talking about the zero flag. Okay, whether or not the zero flag will be set. Okay, so that would be one example. Again, feel free to ask if you have any query. Okay, feel free to ask if you have any query. Don't let your queries go without being answered. All right, so let's see another example. Okay, maybe, and this is a very popular example, and rather I would say this is kind of a useful example. Say I like the previous example, say I did MVI A, comma 57, something like that, MVI B, comma 57, something else. So these numbers could be anything. Okay, sometimes we need to compare two numbers. Right? Compare the content of A with that of registered B. So what number is stored in A and what number is stored in B, we are comparing them. So the instruction is CMP. We are saying CMP B. So this instruction compares the content of register A with that of register B. Okay, this instruction compares the content of register A with that of register B. And of course, whenever we are comparing two real numbers, there can be three possible results, right? There can be three possible results. Either A can be greater than B, or B can be greater than A, or they can be equal, right? Now, we shall talk about the compare instruction later on when we actually talk about it really. Okay, but for the moment, say try to understand, if A and B are equal, okay, if A and B are equal, then after executing the compare instruction, the zero flag becomes 1. The zero flag becomes 1. The zero flag gets set when these two numbers are identical. Okay, so compare instruction is also one of the instructions where the zero flag will be affected if the numbers we are comparing are identical. So under the hood, this is like the compare instruction is probably doing some subtraction. After the subtraction, if it sees that the result of the subtraction is 0, then it sets the zero flag, right? Something like that is happening under the hood. That is why the zero flag is set when the two numbers we are comparing are identical or are equal in nature. Okay, so that's another example where the zero flag would be set. Okay, again, feel free to ask if you have any query. That's another example where the zero flag would probably be set. Okay, all right, let's see another example where the zero flag would be set, and this is quite a kind of a prominent example. I mean, very quite often used. Okay, say we would set a register probably. Okay, so how do I set a register? Using MVI, of course, or by some other means. Say MVI B, comma 03. So what is the value of this register A or this register B? It's 03, right? Now for some reason, okay, and we shall see why. For some reasons, I might want to decrement the value of register B, right? Maybe I want to do something 3 times, okay, and I'm keeping a count of that. Maybe I want to do something 3 times and I'm keeping a count of that, all right? So if I want to keep a count of something, okay, what would I do? I would set a counter. Okay, I would set a counter, and this is the counter. For example, say I want to multiply a number with 3. So what can I do? Simply I can take the number, okay, and add it 3 times, right? So I would have multiplied the number with 3, for example. So I would set a counter to 3, and every time I have done an addition, okay, so I would decrement the counter by a value of 1. So for example, I wanted to do something 3 times, so I would, after doing it once, I would decrement the counter. So of course, decrementing a single register here has a instruction of DCRB, so that decrements a single register. Okay, so after doing DCRB, what happens? Register B decrements, becomes a and it attains a value of 2. Then if I do DCR once again, it gets a value of 1. And if I do a DCR once more on register B, the register B would now have become 0, 0. Okay, and after decrementing, if the register becomes 0, then the 0 flag is also set. That indicates whether this counting operation has finished. Okay, so through this DCR instruction, and before that by setting a register to a certain predefined value, you can make sure that you are executing a loop a fixed number of times, and we shall use this kind of idea to execute a loop very shortly. Okay, so after doing this, since B will become 0, okay, so again this is an arithmetic operation, right? We are decrementing a number, so subtracting 1 from a number. Okay, so this is an arithmetic operation, and with this arithmetic operation, when the number becomes 0, the 0 flag also is set. So so at this point, B equals 0, and thus the 0 flag is set. 0 flag is set. So 0 flag will indicate that, of course, the result of the last executed instruction was a 0. Okay, something like that. Something like that. So this is another example where the 0 flag would be set. There is a question. If two values change to 0, yes, so there is a question like if two values change to 0 at different times, right? Okay, so the thing is, after doing an arithmetical logical operation, okay, only one value can change as such. Okay, as such, only one value can change. There are certain data transfer instructions where more than one values can change all at the same time, but data transfer instructions won't affect the 0 flag. Okay, data transfer instructions won't affect the 0 flag. Apart from that, if you are executing some arithmetic or logical instructions, only one value will be affected at the same time. So you cannot really affect more than one register all at the same time. Right? I mean, not one register, but more than one value again. Maybe a register pair or maybe a register, something like that. Okay, so at a time you cannot affect more than one thing per se. Okay, you get the point, get the idea, right? So with that said, at one time you can only affect one register, right? So for example, after that, if I had some some other register has been also decremented along with this, okay, so then after executing a certain instruction, okay, the moment this instruction is executed, the 0 flag will be automatically set. Okay, but then if there is some other instruction after this, the value of 0 flag will become different after the next instruction, probably, right? So the flag register only indicates the status of the last executed instruction. Got the point, right? The flag register indicates the status of the last executed instruction. So last executed instruction might have a carry, but if you execute something else right after the last executed instruction that resulted into a carry, the carry flag will probably be cleared or something. Okay, got the point? The flag register only keeps track of the status of the last executed instruction. Okay, so if after this something else happened, the result of that instruction will be reflected, or rather the status of that instruction will be reflected into the flag register, and whatever was the result of this register, okay, whatever was the result of this, or rather whatever was the status of this instruction, will be completely forgotten by the flag register. So the flag register only keeps track of the outcome of the last executed instruction, or the status of the last executed instruction. Okay, So right now, if you are looking at the flag register will indicate what happened when the last instruction was executed. Okay. And right now, if you are just executed another instruction, then the flag register will now reflect what the status of the instruction that you just executed. So flag register does not keep track of everything. It just keeps track of the last executed instruction. It just keeps the status of the last executed instruction. Whatever happened just now, like that. Okay. So what happened long ago, it does not care to remember. So yes, your answer is, yeah, nothing will happen. Or it will only keep track of whatever happened last. So I think I answered your question. Please again, feel free to ask if you are still in doubt. Okay. All right. So with that said, let's move forward. So we have talked about the zero flag, right? And now we have two flags that are, used, but not that much. Okay. One of them is the parity flag, and the other of them is the zero sign flag. Okay. Now, how many of you know that numbers can be signed or unsigned? Okay. What is a signed number? And again, half of this class is going to be on Boolean algebra and such. Okay, we are still talking about algebra and so on. All right. So please let me know how many of you understand the signed integers. How many of you understand how signed integers work? Okay. Or how do you actually define or model negative numbers using binary? How many of you know how to define negative numbers? How do you define negative numbers? Are you aware how you define negative numbers? If not, please let me know. I will just have a short discussion on that. Then we shall switch. Please let me know. Please let me know if you understand how negative numbers work in binary. Again, you just have to confirm that whether or not you understand how negative numbers work in binary. If you do understand, I will just skip over. If you don't, then I will proceed. Oh, unfortunately, with binary numbers, you cannot add a negative sign. Okay? You cannot add a negative sign with a binary number. So let's have a small discussion on negative numbers. Let's have a small discussion on negative numbers in binary. One of you just got the other way around, got it other way around. Okay, let's discuss. Let's discuss how negative numbers really work, because we have to have a concrete idea about everything. And again, I'm not in a hurry to complete the entire syllabus, right? So whatever I teach here, I want it to be completely understood. So that is what I'm interested in, right? And I think you should also too. Yeah, unfortunately, yes, you can have an. It is not like just that. It is not just that. We shall soon see. Some of you are saying that add one for negative sign. Yes, your ideas are, kind of there. It indicates that you probably have studied it at some point in your life, but you have completely managed to forget this, right? So let's have this discussion right now. All right. So no, not really. You don't add one for a negative sign or anything. Okay, let's see. Okay, say we only have positive numbers. say we only have positive numbers. So if that, what is the minimum positive number? So that would be 0 0 0 0 0 0 0 0 in binary, right? So that indicates this is 0 in decimal, right? That's 0 in decimal, right? And what is the largest binary number that you can have in 8 bits? That's 1 1, that's 1 1 1 1 1 1 1 1, and that's 255 in decimal, right? In decimal, that's 255. So if you are just only content with 8-bit numbers, or if you are just have to deal with 8-bit numbers, what is the minimum 8-bit number you can think about? That's 0 0 0 0 0, all zeros, right? In hexadecimal, that would be 0 0 hexadecimal, right? And in binary, what is the largest number you can have in 8 bits? That would be 1 1 1 1 1 1 1 1. That would be FF in hexadecimal, right? That's the largest number you can have. So smallest number, largest number. But what if you are talking about signed integers? This is known as unsigned integers. Unsigned integers. So these are all integers, but unsigned integers. Unsigned means there is no sign associated with this. All the numbers are positive. Okay, signed integers. All the unsigned integers are integers that are always positive, right? Unsigned integers. So there is no negative sign anywhere to be found. Okay, so that's unsigned integers. Now, whenever we are talking about signed integers, what happens is out of these 8 bits, only the last 7 or the 7 least significant bits are used. So 7 lesser significant bits are used. So this is kind of reserved under this category. Okay, whenever we are talking about unsigned signed integers, this is, so the discussion is on signed integers. Okay, so whenever we are talking about signed integers, this bit is reserved. Okay, so this is the 0th bit, first, second, third, fourth, fifth, sixth, 7th, and the 7th is a reserved category bit at this point. Okay, so you can have your number as much as many numbers as you want, probably using this 7 bits, 0 through 7. Okay, 0 through 6. Out of these 7 bits, you can write whatever you want, and this bit will indicate the sign of that particular number. And how does that really work? Let's try to figure out how it really works. Okay, let's try to figure out. Okay, got the point? Right. So give me any number, please give me any number. Write something on the live chat. Give me any number that can be represented as a 7-bit binary. Give me a positive number that can be represented with a 7-bit binary. So nothing more than 127. Give me a number below 127. Give me a number. The idea is we have to understand everything, right? And understanding binary number system is very important here. Okay. Oh, some of you just given me a number which is itself in binary. Okay, fantastic. Since you are the first one, I have to respect your number. So what is 0 1 0 0 1 0 1 1 0? Fine. 0 0 1 0 1 1 0. Okay. So the first order of business is to figure out what is this number in decimal. Okay. So again, this is being kept as reserved. I don't really want to use this because I want to treat signed integers. So I have to have I want to have a negative sign, right? Get this idea, right? I want to have a negative sign. So I'm going to figure out how to treat negative signs, because try to understand. So this is going to be stored in a memory, right? In a memory, and in memory you don't have anything that indicates a negative sign, right? It is only 0 or 1, something like that. Okay. So with that said, some of you saying 125. So I have already written this number, right? So so let's copy this and say paste it here. Okay, so this is an example, right? So I just copied everything over. So this is in binary. Of course, in decimal, what is the number? In decimal, what is the number? Can anybody tell me what this number is? I think it's very easy to understand. Okay, so again, the positional values of each number here are the as such. Okay, this is 1, this is 2, this is 4, this is 8, this is 16, this is 32, this is 64. Okay, these are the positional values of these numbers. Okay, so this has a value of 0, this has the value of 2 right now, this has the value of 4, so we have a 6, this has the value of 16, so 16 plus 6, right? So that's the number. So 16 plus 6, that will be 22, right? So this number is 22 in decimal. So I'm writing a 10 in subscript, means it's a decimal number, 22, right? So now I want to figure out what would minus 22 look like, right? I want to figure out what is minus 22 going to look like. Get the point, right? I want to figure out what is minus 22 going to look like. And why am I thinking about minus 22 at this particular instance? I'm thinking about minus 22 because I want to figure out that number when added to this, the result becomes 0. Get the point? I want to figure out what minus 22 would look like in this binary system, right? So that I have some idea about negative numbers, and nothing is ad hoc here. Okay, I want to figure out that binary number, okay, that when added to this number gives you a 0. And what number added to this would give you a 0? That's of course minus 22, right? Minus 22 when added to plus 22 would give you a 0. So now let's see what would minus 22 look like in binary. And again, we are talking about 7-bit binary here because this is now going to be reserved. And why is this reserved? We shall soon understand why this is reserved. But for the moment, let's figure out what we are trying to do. So this is our number here. This is our number, right? This is our number. So what is the number? In again 7-bit binary, the number is 0, 0, 1, 0, 1, 1, 0, right? So again, if you have any query, feel free to ask at this moment because we are kind of going to move forward quickly, right? So now my objective is, this is 22. We are trying to figure out what minus 22 would look like. We are trying to figure out what minus 22 looks like, right? So now let's do something called ones complement on this. Let's do ones complement on this, right? So we are doing two operations here. We're going to do two operations quickly. Now let's do ones complement on this. And how do I do ones complement? I just write 1, 1, 1, 1, 1, 1, 1 and subtract, right? Subtract. Of course, right? So I have 1, I have 0, 0, I have 1, I have now 0, I have 1, 1. That's a ones complement of 22. Try to understand. So this is ones complement of 22 decimal. That's ones complement. Now of course, try to understand that this is not how the computer does ones complement. Okay, if you ask a computer to do ones complement, it does not subtract. It does not subtract. Okay, but for it, doing a XOR operation is easier. Okay, how does the computer calculate ones complement? It simply takes the number and XORs it with 1, 1, 1, 1, 1, 1, 1, 1, something like that. Okay, so what is the XOR of 1 and 0? That's 1. What is the XOR of 1 and 1? That's 0. What is the XOR of 1 and 1? 0. What is the XOR of 1 and 0? 1, and so on, right? Something like that. That is how the computer actually calculates ones complement. But for us, this is what ones complement is, right? Now, along with this, let's calculate twos complement. And we shall soon see where we are actually going with this. Okay, let's calculate twos complement. And how do I calculate twos complement? By just adding 1 with everything, right? If I add 1 with everything, I would get now twos complement. Okay, twos complement of what? Twos complement of 22. Okay, so what if I add twos complement with this? Let's push this, right? So what if I add twos complement with this? So add 1 and that gives me twos complement. Let's see what is twos complement here. So if I do that, so 1 plus 1, that gives you 0, and you have 1 here. Of course 1 is carried over, so that gives you 1, and then we have a 0, then we have a 1. Okay, then you have a 0, we have a 1, we have a 1. Okay, right? So is there any problem with this? Please feel free to ask if you think there is a problem with this. All right. Let me see. All right. So is there any problem with this? No problem, right? So I'm now saying this is 2's complement of 22. So far we have treated 2's complements and 1's complement in 7 bits. Why? Let's just consider complements in 8 bits, because the microprocessor at the end of the day can only talk about 8-bit numbers, right? Here. So let's do the complement with 8 bits. So if I do that, I would have a 1 here in addition to this. I actually really wanted to do this in another step, but let's do this right now. So that is what the 2's complement of 22 is. So is there any problem with this? No, right? There is no problem. That's the 2's complement of 22, right? So now let's add 22 with its 2's complement, right? So what was 22 in binary? So 22. What was 22 in binary? So of course we wrote that. That was, so now of course I am keeping this vacant, right? So by default I won't write anything here. And so if I don't write anything here, what would I consider by default? By default I consider a 0 to be here, right? Since this is vacant, I would consider a 0 here. So the number is 0, 0, 0, 1 and then 0, 1, 1, 0. 0, 1, 1, 0. And now I am adding 2's complement. 2's complement of 22. So 2's complement of decimal 22. So what is 2's complement of decimal 22? That's this number. That's 1, 1, 1, 0, 1, 0, 1, 0. That's this number. So what if I want to add these two numbers? So I'm doing an addition on these two numbers. Okay. So if I do add these two numbers, what do I see? What do I really see? Okay. What is the sum of these two numbers? Try to figure out. So 0 plus 0, that gives you a 0. 1 plus 1, that gives you a 0. We have a carry 1. So again 1 plus 1. Okay, 1 plus 1 because of that carry. So I have a 0. Again we have 1 carry. So 1 plus 1, that gives you a 0. Okay. So again we have 1 carry. So 1 plus 1, that gives you a 0. Again we have 1 carry. So 1 plus 1, that gives you a 0. Again we have 1 carry. So 1 plus 1, that gives you a 0. Again we have 1 carry. So 1 plus 1, that gives you a 0. And again we have 1 carry. That goes outside. That goes outside. Now this is the result. So if I only have 8 bits with me, if I can store only 8 bits of numbers in my register, okay, so using 8 bits, what is the sum here? What is the sum here? And again, this will be reflected in the carry flag. So this will set the carry flag for my particular scenario. Okay, this will set the carry flag. But my point is, what is the result? What is the sum of these two numbers? Forget the carry. What is the sum of these two numbers? The sum of these two numbers is 0. Try to understand. The sum of these two numbers is 0. Right? Right? So now let me ask you the same question. 22 is a positive number. What is the number that I need to add with 22 so that I get a 0? The answer is minus 22. Again, question is, 22 is a positive number. What is the number that I need to add to 22 in order to get a 0? The answer would be minus 22 in our simple decimal operations, right? But in binary, we don't have negative numbers, right? Because we cannot store negative numbers as such, right? We can only store 0 and 1. There is no place for storing a minus sign, right? There is no place for that. So how do I indicate minus 22? So this is minus 22, right? And how did I indicate minus 22? Again, we are only considering 7 bits of number. So how did I indicate minus 22? We indicated minus 22 by the 2's complement of 22. So this was 22 and this was 2's complement of 22. Now look very carefully. In the 2's complement, in the number 22, okay, the most significant bit was 0. And in the 2's complement of 22, the most significant bit is 1. But the rest of it is the 2's complement of this number. Okay? Got the point? So now if I ask you, what is the, so in signed integers, what is this number? Okay, in signed integer, how would you deal with this number? By taking this in hexadecimal. Okay, in hexadecimal, what is this number? This number is 1 and this is how much? 6, right? 16 in hexadecimal, right? Right? At a signed integer. And what about this number? What about this number in terms of signed integer? Okay, again, whenever we are talking about signed integers, we have to take 4 and 4. So hexadecimal again. So what is this number? This is 8 for 12, 13, right? Right. All right. So that's E. This is E and this is 8, 9, 10, A. Right? If these were not signed integers, they will be treated as unsigned integers and this would just be 16 hexadecimal. This would be EA hexadecimal, right? Now, this is again a signed integer. Okay. And how do I understand that? I understand simply by the fact that the numbers cannot be greater than 255. Greater than 127. Try to understand again what I'm saying here. Okay. So with that said, if these two numbers, if for example, if EA, that's a hexadecimal number, was in unsigned integer space, unsigned hole, if this was unsigned integers, if this was unsigned, then what would happen? This would be treated as E. What would this number be? Again, this is 14 into 16 plus 10, that much. Okay, that much. So let's open up a calculator. How much this number is? Hold on. Okay, all right. This is going to be 234. Right? But EA, when this number is treated as a signed integer, is going to be minus 22 in decimal. Right? So do you get the difference now? Okay. Now this number is going to be minus 22 if we are talking about signed integers. Okay. So this is the 2's complement of some number. What was that number? That number was 22. Right? So of course, what indicates that it's a signed integer? Okay. What indicates that it's a negative number? The indicator is here. This is what indicates that it's a negative number. This is what is responsible for indicating that it's a negative number. Okay. So this indicates that this is a negative number. But the rest of it is 2's complement of the number that we negated here. Okay. That we negated here, right? Rest of it is the 2's complement of the number we negated here. All right. All right. So I have questions for you. Okay. So now, what is the largest number we can have? So again, feel free to ask if you have any query regarding anything. Let's now let me draw a table then. So in the table I have binary, then I have hexadecimal, and there if the number is considered signed, and again it's entirely up to us whether we are treating signed numbers or unsigned numbers. Okay, hexadecimal number, and this is the signed, and this is the so this is unsigned, this is signed. Okay, all right. So again, try to understand what I'm saying here. Okay, if the number is 0000 and 0000 in hexadecimal, this is 00. In unsigned integer, unsigned, okay, hexadecimal, this is unsigned in decimal, right? In unsigned, this is again 0. In signed, this is also 0, right? Similarly, if this is 0000 0001 in hexadecimal, this is 01. In unsigned integer, this is also 1. Unsigned decimal, I mean, this is also 1, right? Understandable, right? Similarly, so and so on up to 0 1 1 1 1 1 1 1. So this is 7f, right? 7f. So this is in unsigned space, this is 127, right? This is 127, right? All right. Now what is the next number? Next number is 10000000, right? This number, of course, you can understand this is 80, right? In hexadecimal, this number is 80 in hexadecimal. If this was unsigned, right, this would be 128, right? This would be 128. But if we are considering signed integers, okay, then this number is indicative of a negative number, right? This number is indicative of a negative number, and this sign is indicating that it's a negative number, okay? And the rest of it is the 2's complement of something. Question is, what is that something whose 2's complement is 0000000? So all these 0. What is that number whose 2's complement is this? What is that number whose 2's complement is this? Can anybody shed some light on this? What is that number whose 2's complement is this? Whose 2's complement is this? I'm trying to figure that out, because that is going to be the number, right? So this is going to be minus something, of course, a negative number, because I have a 1 here. And whose 2's complement is this? Whose 2's complement is this? So the whole number is the 2's complement of somebody. Question is, whose 2's complement is this? So can anybody shed some light on this? So it is somebody's 2's complement, right? This number is someone's 2's complement, right? So this is the number we are treating here, 10000000. It is someone's 2's complement. So let's subtract 1. So I will get the number whose 1's complement. So right? No, it's not 0000's 2's complement. So it is 1. So this is some numbers 2's complement, right? This came as the 2's complement of some number, right? So now if I subtract 1 from it, so what is the number? 0 1 1 1 1 1 1 1. So this is the 1's complement of something, right? This is the 1's complement of something. Is that understood? This is the 1's complement of something. And if this is the 1's complement of something, okay, try to understand. If this is the 1's complement of something, what is that something whose 1's complement is this one? What is that something whose 1's complement is this one? So we have to do 1's complement once more, right? What is that number whose 1's complement is this one, right? In 7 bits, of course. What is that number? No. Yeah, this is fine. So, right? This is the 2's complement of some number, right? And if I subtract 1, then this is the 1's complement of that number we are looking for, right? Question is, what is that number whose 1's complement is this one? All we have to do is to do the 1's complement once again on this, but with 7 bits, right? So if I do ones complement on this with 7 bits, all right, so all I have to do is to write down 0 1 1 1 1, sorry 1 1 1 1 1 1 1, and subtract this minus this one 0 1 1 1 1 1 1 1. So this is how we calculate the ones complement in 7 bits. That gives you 0 0. All right, so in hexadecimal. So with this entire calculation, all I know right now is that this number here in the 7 bits, this number, this came as a ones complement of, so rather two's complement of 0, right? Two's complement of 0, right? Try to understand. So this came as a two's complement of 0, right? So this number, but so would I say negative 0 here? What is the point here? Is it negative 0 here? So if I write something here, would it be negative 0? So please tell me if you understand this. Is this going to be negative 0 or not? So what is the point here? What is the number that I have here? What is the number that I have here? Then again, just go back to our previous discussion here. In our previous discussion, what did we discuss? We had a number, right? And that's resulted into a two's complement of some other number, right? So that when added to this, we got added to itself, we got a 0, right? So EA, when treated as a two's complement of some number, we get a 0, right? So yes, so EA was two's complement of minus 22, so 22. So we added these two numbers, so we got a 0, right? So we got a 0. So what is this number then? What is this number? What is this number? Can anybody tell me? This cannot be 0, right? What is this number then? So can anybody tell me? I can tell you very quickly. Okay, okay, let's think about this. What is 128? It's rather plus 128. What is plus 128? Of course, decimal. What is that number? What is that going to be? What is plus 128? Please let me know. What is plus 128? Plus 128 is 1 0 0 0 0 0 0 0, like that number, right? All right. So what is one's complement of plus 128? What is one's complement of plus 128? What is one's complement of that? Tell me. So that is going to be 0 1 1 1 1 1 1 1. So what is two's complement of plus 128? What is two's complement of plus 128? Add 1 with this. So what do I get? 1 0 0 0 0 0 0 0. So this is two's complement of plus 128, right? So question again, what is this number then? This is two's complement of plus 128. So this is minus 128, right? So negative numbers are just two's complement of their positive counterpart. So this is minus 128. Get the point? You get the point, right? All right. So what is the next number? So 1 0 0 0 0 0 0 1. Again, we are considering signed numbers. So again, in hexadecimal, that's going to be 8 1, right? Now in decimal representation, unsigned decimal representation, that's going to be 129. Now here we are now again trying to figure out what is that number for which this is the two's complement. Of course, if you do a little bit of calculation, you will see that the number whose two's complement is this one is this 127. So this is minus 127. So this is the representation, minus 127. So take 127, convert it to binary and do two's complement, you will get this. With that said, let us erase everything. Okay, so again 1 0 0 0 0 0 1 0, right? That's going to be 80 2 in hexadecimal. Of course, again in hexadecimal there is no question of putting a negative sign or positive sign, right? We cannot do that. Okay, now this is going to be 130 as far as our decimal unsigned representation is concerned, and this is going to be minus 126 and so on. So the largest number would be here, would be 11111111, right? And that's going to be FF in hexadecimal, okay, right? And if we are talking about unsigned integers, that's going to be 255, right? Now, of course, whose 2's complement is this? Whose 2's complement is this? Can you repeat me whose 2's complement is this? So whose 2's complement is this one? What is the number that has a 2's complement of 1 1 1 1? All of them are 1. The answer is 1. So this number is minus 1. So let me again show you. So if I have just 1 plus 1, right, in hexadecimal, in decimal. So if I have plus 1, the number would be 0 0 0 0 0 0 0 1. Then what is plus 1's 2's complement? So 1's complement. What is plus 1's complement? Just this one. Try to understand. This is going to be 1 1 1 1 1 1 1 0. Then what is plus 1's 2's complement? Okay, add 1. So I have 1 1 1 1 1 1 1 1, right? Right? So this is 2's complement of plus 1. So this is minus 1. So that is how the signed number space actually really works in our computers per se. So again, feel free to ask if you have any query regarding anything. That is how signed numbers work. So in 8 bits, so if I say, therefore, in 8 bits, unsigned integers numbers are from 0 to 255, right? 0 decimal to 255 decimal. But in 8 bits, signed numbers are from minus 128 to plus 127. See, we have 256 numbers. How many numbers do I have? 256. Okay. So how many numbers do I have? I have 2 to the power 8 numbers. But half of them are positive, half of them are negative. Okay. So 0 to 127 in the right hand side and minus 1 to minus 128 in the left hand side. That's how we have represented positive and negative numbers. Right. We had been talking about flag registers, right? So please feel free to ask if you have any query. All right. So our point was, what is this? What does this sign flag do? This sign flag indicates, this sign flag is set to 1 when the result of executing an instruction is negative. After executing an instruction, if you get a negative result, so if the most significant bit is equal to 1, okay, so and if you are treating them as signed numbers per se, okay, under that scenario, okay, if the result of executing a number is negative, okay, then the sign flag is set. So this is known as the sign flag. Okay, so let's now go back here. So example where sign flag is set. Let me show you a very simple example once again. Okay, so moments ago I showed you how to compare two numbers, right? Comparison is a very good example where you get to see how the sign flag really works. Okay, so if I do MVI A comma, say for example 75, and MVI B, if I do MVI B comma, say for example 85, understandably of course B is larger than A, right? Now if I compare these two instructions, compare B, these two numbers. If I say CMP B, what happens? The number stored in register B is compared with register A by means of an internal subtraction. Internally, it subtracts the content of register B from that of register A and figures out whether the result is a 0 or not. Now, of course, the result will be 0 and a 0 flag will be set if these two numbers are identical in nature. But what if B is larger than A? When B is larger than A, so when content of A is smaller than content of B, so that when B is larger than A, what happens? The result is apparently a negative number, right? So the sign flag would be set. So the sign flag would be set. So when you are comparing two numbers, you can actually look at the 0 flag and the sign flag, and based on that knowledge, you can figure out whether the two numbers are positive or negative. So let me show you a concrete example of what I just said here. For example, if I do MVI A comma 75 and if I say MVI B comma 75 and I want to compare these two numbers, right? And just like in many if else statements, we compare numbers, right? We compare. Okay, so if I say CMP B, this possibly has three results. CMP B possibly has three results, right? Under this scenario, when these two numbers are identical in nature, so since content of A is identical to that of content of B, what would happen? Sign flag will not be set. Sign flag will be 0. Okay, because the result isn't negative in a sense. Okay, and the carry flag and the 0 flag would be set. So by looking at the sign flag and the 0 flag, we would be able to understand that these two numbers are equal, right? These two numbers are equal because under the hood it did some subtraction and the subtraction resulted into a 0, and because of that we would know that the 0 flag has been set. Okay, by looking at the 0 flag, in a way we would be able to see that yes, this result must have been so because these two numbers were identical, right? And sorry, right? So let's see another one where I have, let's move it. Okay, let's see another one where I'm doing something like this. I am doing MVI A comma 75 and MVI B comma 65. So of course register B is smaller, the content of register B is smaller than content of register A. So if I do compare B, of course under the hood a subtraction happens, but inside the subtraction, try to understand, since A is greater than content of A is greater than content of B, the subtraction would neither result into a 0 nor a negative number. So the sign flag will be 0 and the 0 flag will also be 0. The 0 flag will not be set, the sign flag also will not be set. So from this knowledge, we would be able to figure out that the content of register A was indeed larger than the content of register B, right? All right. Now let's see the last one where we have something like this, where we have MBI A comma 75. So the number stored in register A is 75. Okay, and MBI B comma 85, something like that. I'm just choosing 75, 85 at random, right? Just some circles. So if I now compare the content of register B with that of register A. Now under the hood a subtraction takes place. So A minus B, and the result is of course now negative. So with that said, since content of register A is less than content of register B, what will happen? The under the hood subtraction will result into a negative number. So the sign flag will be set. Probably something will happen to the carry flag as well. Okay, but that's not our concern right now. But the 0 flag will also be 0 flag will not be set because the result wasn't 0, right? So now after doing the comparison operation, by looking at the status of the flags, we can figure out what exactly happened. We can figure out which one of these numbers are bigger and which one of them is smaller. by looking at the status of the flag registers. So feel free to ask if you have any query regarding this, because we use this knowledge of flag register in order to employ conditional logic. And by conditional logic I mean writing if else, for example writing loops. Okay, and if else and loops, they do use the jump instruction rather the conditional jump instruction, so you'll see. Okay, and by looking at the conditions that can be seen from the flag register, we can do certain operations. Okay, so kind of executing if else statements. Okay, if I want to do if else, for example, using this assembly language programming, what we are going to do, we are going to use conditional jumps. Okay, right? So far whatever we have discussed so far, feel free to ask if you have any query. Again, we are going to continue this discussion into the next class, but today whatever we have discussed so far, feel free to ask if you have any query so far. Again, feel free to ask if you have any query. I promise to take 20 more minutes, not more than that. So I'm constantly monitoring the live chat. Feel free to ask any question that you might have, or else we shall proceed from this. We just skipped a flag, which is the parity flag, and we shall talk about that, come back to that. And the P flag was the parity flag. We shall talk about that later on. We shall talk about parity flag later on. I mean today, later on. Again, this is quite rarely used. The important things are the sign flag, the zero flag, the carry flag. These three are quite used a lot. So feel free to ask any question that you might have, or if you have understood everything, feel free to let me know. Okay, so one of you have a very interesting question. So that whether if we're doing just unsigned integer operations, will the sign flag still work? Yes, actually the sign flag always works. Whether or not you are treating the numbers as signed integers or unsigned integers, it's up to you as the programmer. Because as the program is concerned, every number is represented in hexadecimal like that, right? As far as the microprocessor is concerned, all the numbers are represented in hexadecimal, right? All the numbers look like this. But whether or not you are going to treat this FF as 255 or -1, it's entirely up to you as the programmer, right? So as the microprocessor is concerned, rather as the computer is concerned, FF is nothing but 255, right? So the number is FF, right? But whether or not it's going to be -1 or 255, that's entirely up to you. Okay, So when the microprocessor sees this number, it treats this as FF. Okay, but what this number means to you, it's up to you, and you have to program accordingly. Whether you are treating unsigned integers or whether you are treating signed integers, based on that you have to write your program. Okay, by looking at the sign flag and such, right? But the microprocessor makes no distinction between signed integers and unsigned integers. You have to make that distinction yourself, because the microprocessor has absolutely no way of knowing really whether you are talking about signed numbers or whether you are talking about unsigned numbers. It only looks at the most significant bit after executing a program. Okay, and if the most significant bit is equal to 1, it tells you the number is probably a negative number. If the most significant bit is 0, okay, then it tells you the number is probably a positive number. That's what it does. But whether you are treating the most significant bit as a part of the number or as a part of the positive or negative sign, it's entirely up to you as the programmer, right? You get the point. The microprocessor has no way of knowing that. It only checks for the most significant bit. If it's 1, it sets the sign flag as 1. If it's 0, it sets the sign flag as 0. Okay, so sign flag equal to 1 means the most significant bit is equal to 1. But whether the most significant bit itself is a part of your number or is it a part of the positive or negative sign, it's entirely up to you as the programmer. So if you are treating that most significant bit as the part of the sign, then of course it's a negative number and such, right? But in any case, microprocessor makes no distinction. You as the programmer will have to make that distinction for yourself. Again, feel free to ask if you have any query. All right, so since we don't have any more queries, let's clear up the question on parity flag. What is a parity flag? Let's do a simple calculation. Okay, let's switch to screen. Yeah, right. So let's do this. So again, if you recall, our program always starts with origin. For example, I'm starting my program from this memory location 8050, setting my program counter to start from 8050 memory location, and let's do this mvi a comma 55 some value, right? So this is a simple program, right? So this program just has taken 55 and copied it over to accumulator. So this is a 2-byte instruction. It has 2 machine cycles, output fetch, memory read. That's it. Okay, so I'm demonstrating the parity flag momentarily. Okay, let's assemble this program. So if I assemble this program, okay, so let's do that. Okay, move forward. So this happened. Okay, right. So the accumulator now has 55 as the number. Okay, now 55 in binary, this representation is also there. What is it in binary? Look very carefully. Okay, what is it in binary? It's 0 1 0 1 0 1 0 1. Okay, got it? Okay, so this is look at the number in binary. Question is how many ones do you see in the accumulator? So in the accumulator, how many ones do you see? Do you see an even number of ones or a odd number of ones? You see an even number of ones, right? You see an even number of ones. So when there are even number of ones, binary ones in the accumulator, it's called an even parity. And when there is an even parity, the parity flag gets a value of 0. Okay, so let me write down what I just meant. Okay, so as far as the discussion with the parity flag goes, okay, so this is the parity flag. What is parity? So there are 2 parities, even parity and odd parity. Okay, and you might already have learned that parity, this kind of things are used for error checking. Okay, so we shall soon realize what I mean by error checking. Okay, even parity means there are even number of ones in accumulator. So in the accumulator, if there are even number of ones in the binary representation, okay, then it's called an even parity. And odd parity means that there are odd number of ones in the accumulator. And as such, if even parity occurs, so currently in the accumulator, if there are even number of ones, then the parity flag will be not be set. So this is often called even parity. And if there are odd number of ones in the parity flag, okay, so if there are odd number of ones in the accumulator, the parity flag will be set. This is known as odd parity. So that's how parity really works. Okay. All right. So let's see the example. All right. So let's see that. So now look at this one. So in the accumulator, how many ones do I have? I have only an even number of ones. So it was an even parity. Okay. So after any execution at any given time, okay, the number of ones present in the accumulator gives you the result of the parity flag. Okay. So for example, if I now make it 56 and assemble this, okay. 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 So there are still even number of ones, right? Let's try making this odd number of ones. All right. Somehow in this software the parity flag isn't working, but in any case, just keep that in mind. What I just said here. Remember the discussion, right? That will be okay for you. All right. I have to check this. The parity flag details. Why isn't it working? Anyway, in any case, we don't really use the parity flag that much. We shall soon see later on. Okay, so that was our discussion on parity flags in any case. So forget that. Okay. Now, how do we execute? Question is, how we run conditional statements. In accurate frame. Okay. So this is how we run conditional statements. So we look at the flag register. Okay. We look at the flag register, and by looking at the flag register, by looking at the current status of the flag register, we figure out what to do. Okay. And to do that, there are jump instructions. So we are going to shortly talk about that. So there are few jump instructions, and out of these, and surprisingly I remember everything. Okay. There are few jump instructions. So, and jump instructions are this. There is JMP. This is known as unconditional jump. Okay. Unconditional jump, and we shall see what jump instruction means and how they work. Then we have JC. So jump if carry flag has been set. Then we have JNC, stands for jump if carry flag has not been set. Then we have JZ, stands for jump if the zero flag has been set. Then we have JNZ, stands for jump if the zero flag has not been set. Okay. Then we have JPE, so jump if parity is even, JPO, jump if parity is odd, and we talked about what I mean by odd parity and even parity. JP stands for jump positive, so jump if sign flag is 0, so the result is apparently positive, then jump positive. And JM stands for jump minus, so if jump if sign flag is set. So these are all the jump instructions in 8085 microprocessor. So you have unconditional jump, you have jump if carry flag is set, jump if no carry flag is set, so jump if not the carry flag is not set, jump if the zero flag is set, jump if not the zero flag is not set, jump if the parity is even, jump if the parity is odd. And I think I have just messed up the parities concept. It could be the other way around. We shall see later on. Okay, I might have just misspoke. That's not our concern. Okay, we can do programming and figure out what it means. Okay, I might have told you this the other way around. The idea is the same nonetheless. Okay, and then we check for whether the number is positive, result is positive. So jump positive, jump minus, not jump negative, but jump minus. So it checks the sign flag. So you can understand we don't have to separately check the carry flag and everything. Okay, and carry flag is written as CY. Okay, all right. So we can execute any of these jump instructions based on what we need, and using that we can do conditional statements. We can do conditional statements, right? So let's see our a simple program where we add two numbers that might or might not have a carry. Okay, that might or might not have a carry, and accordingly we do some condition checking based on that. Okay, and with that we shall store the carry. If there is no carry, we shall not store the carry. So let's see a program on that. And again, so these are all the jump instructions. Okay, again JMP is an unconditional jump. This is designed to create infinite loops. Okay, and I am suffering from allergy for quite a few days. All right. All right, so let's write a simple program, and just like the previous day's program, whatever we did in the last day, so we shall have some numbers stored in some memory locations. So we shall have some numbers stored in some memory locations. So say 3, 4, 5, 6. So starting at this memory location, we shall have some numbers. Okay, so we're going to add two numbers here again. Okay, so we are going to add two numbers, and say the numbers are just like before, say 78 and 95, something like that. Okay. All right, so again we are considering unsigned integers. So let's write a program, very simple program. So I am doing LXI h comma 3, 4, 5, 6. Again we are setting the memory pointer to this, so I am going to do move a comma m, and then inx h. We are going to increment the value of h. Okay, so it points to the next memory address where this number is stored. So I'm going to do move b comma m. Okay, so the content of register m is moved to this. So this number is actually being moved to register b. Okay, this number is being moved to register b, and then we are going to add b. So the content of register a has been added to the content of register b, and the result has been stored in register a. But if there is a carry, so if the sum of these two numbers is higher than 255, so higher than FF in hexadecimal, if the sum of these two numbers is higher than 255, so higher than FF, okay, then what happens? A carry results. Okay, so result is a carry, right? Of course, the result is a carry. So a carry occurs, and how would the microprocessor indicate that the carry occurred after doing this addition? So after doing this addition, if a carry occurs, the carry flag will be set. The carry flag will be set, and accordingly we have to check for the carry flag through a conditional jump instruction. So we will see if the carry flag has been set, we will do something. If the carry flag has not been set, we won't do anything. For the moment, let's recall what we did earlier, we just stored the sum of these two numbers into another memory location, right? So we incremented HL pair again. So now it's pointing to M is pointing to, the memory pointer is pointing to memory location 3458, and there we stored the sum. Okay, so we stored the sum by doing just move instruction. We moved the content of the accumulator into M. But what is M? M is memory location 3458. So there I am storing the content of the sum. Okay, but what if there is a carry? If there is a carry, I have to do something, right? If there is a carry, I have to do something. If there is no carry, I have to do something, right? So if there is no carry, then this is the result. This is the end of the program. I don't have to do anything else. This is the end of the program. If there is no carry, you get the point, right? If there is no carry, this is the end of the program. But what if there is a carry? So if there is a carry, I have to do something in addition to this. I have to do something in addition to this. Got it? To store the carry was 1, would have been 1, of course. And if there is a carry, then I have to, in addition to the sum, I shall also have to store the carry, right? So in order to do that, I have to have a register that stores the carry. So every time a carry occurs, the register gets incremented by a value of 1. So I would initialize the register like this. So I would say MBI, say some register C, 000. Now I am using register C to store the carry. You can use any other register you want apart from H, L, B and M, because they are being used for other purposes, right? H, L, A, B and M. Apart from that, you can treat this as other registers. Now if there is a carry, what I can do, I can check whether there is a carry or not, and based on that I can increment the value of register C. Right? So now after executing this, try to understand, after executing this, if there is a carry, after doing the addition, if there is a carry, I can check whether there is a carry, okay, by doing a conditional jump instruction, right? So if I say jump carry JC, what does it check? It checks for the existence of a carry, right? It checks for the existence of a carry by looking at the carry flag. Okay, and again, this kind of conditional jump instructions and conditional call instructions should appear right next to the instruction that would result into a carry or something like that. So this is the instruction that would result into a carry, and right next to that I have to write down the jump instruction, conditional jump instruction. But if I do it after something else here, the flag will be changed by the next instruction, right? So I won't get the status of this instruction. So in order to get the status of this instruction and do something according to that, I have to put the conditional jump instruction right next to the instruction that I am concerned about. So I am concerned about the instruction addition here. So add B, right? So you get the point. So we added, we are going to add two numbers. So we added two numbers, and if there is a carry, what I can do, I can increment the value of register C. But instead of doing that, that might make our program complicated. So now what we are doing, try to understand what we are doing. We are checking if there is no carry, because if there is no carry, this is going to be the end of the program, right? So I'm saying if there is no carry, go to the end of the program, and this is the end of the program. So again, look very carefully what is happening here. This is the label, and label is nothing but an address. Okay, label is nothing but an address. Okay, look very carefully what is happening here. Again, let me give everything a shift. All right, so I'm saying if there is no carry after this, please move ahead. Please move ahead. I'm saying that, right? Got it? So if there is no carry, please move ahead. Or if there is a carry, then increment INR register C. All right. All right. So what is happening here? After doing this addition, this conditional jump statement is going to check for the existence of a carry. If there is no carry, then it does not need to increment the counter that is keeping track of the carry. It does not need to do anything like that. It needs to make the program counter jump to this and end the program accordingly. So I would end the program with a halt instruction, right? You get the point, right? But if there is a carry, this conditional jump will not take place. Okay, the program counter will not be moved to this. And if there is a carry, what will happen? This is the instruction that is going to be executed. We shall soon see how this actually comes into effect. Okay, so please hold on patiently. Okay, right. So if the carry flag is set, well and good. If it is not set, also good, no problem. So here, now after storing the result into register, into the memory location 3, 4, 5, 8, let's increment the value of register H once more. So in the next memory location, I am going to store the content of flag C, register C. Okay, register C. So what I'm going to do, I'm going to move the content of register C into M, right? So that is what I do. Now let's see this program into action. But again, try to understand what is this end here. This end is nothing but a label. And what is the label? Label is nothing but an address. Label is nothing but an address. So let's assemble this program. Okay, let's assemble this program. Okay, let's assemble this program. And okay, let's go back and let's choose simple numbers that would not result into a carry. Okay, this would result into a carry, but say take smaller numbers. This would not result into a carry when I am adding them. So let me show you. Okay, done. So that's the assembly. So we have assembled the program, right? So of course we are setting the value of C to 0, 0. Again, feel free to ask if you have any query or try to follow properly. Okay, C has been set to 0, 0. And why am I doing this? Everything starts with 0, 0. But there is a possibility that a register might contain some value from the previous execution. That is why it's always a good idea to set everything to 0, 0. Okay, before I start them as a counter or something. Okay. Now, of course, I'm moving forward and I'm doing LXI H, 3456 because my intention is to use the HL pair as the program counter, right? So my program intention is to use the HL pair as the program counter. And thank you. One of my friends and colleagues is here. So so my intention is to use the HL pair as the program counter, right? So with that said, HL pair as the memory pointer. So right. So the HL register pair is now pointing to this memory location, right? And of course my fictitious register M will be, so we discussed this in the last class, will be pointing to this data, right? So that's understood. So if I now move this data over to the accumulator, so now this accumulator has the data that was being pointed by our fictitious register M, and we discussed this in our last class, right? In our Saturday class. So we have this data in the accumulator. Fine. So we are incrementing the value of the HL register pair, and the value of the HL register pair would now be incremented. So now what do I mean by incrementing the HL register pair's value? Again, I am using the HL register pair as a memory pointer again. I'm not using it as a general purpose register here. Okay, I'm using it as a memory pointer again. Now what is the value of the HL register pair? The value of the HL register pair at this point is 3457. Now look at the memory here. So at memory location 3457, what do I have? I have the next data, right, which is 1, 2, right? So now of course that is now being pointed by memory pointer M, right? M is now pointing to that data. So now if I do a move B comma M, what happens? That data is moved on to register B. Okay, so now register B contains that. Again, so this is something we discussed in the last class, right? And now if we add these two numbers, very nice, we added these two numbers, and of course the result, the sum of 78 and 12 resulted into an 8A, and there was no carry. So the carry flag was not set. Carry flag was not set. Okay. Okay. We are only interested about the carry flag, but still I would draw your attention to the sign flag, because one of you asked a question about that earlier. Let me draw your attention to the sign flag. Look very carefully that the sign flag has been set to 1. Why is that so? I am not dealing with negative numbers here, right? Because the microprocessor has no way of knowing that. It does not know whether we are dealing with negative numbers or not. It only saw that in the accumulator, the most significant bit was 1. And based on that knowledge, it told you that the result could be a negative number. That is why it has set the sign flag for us. Because if I wanted to treat this as a negative number, we could, right? We could. And apparently the sign flag has been set just because of that. But again, we are not interested about the sign flag in this particular scenario. We are only looking at the carry flag in this particular scenario, right? Now look at the jump no carry instruction, JNC instruction. Now this jump instruction, of course, comes with a label. But what is the label? A label is nothing but an address. Okay, got it? A label is nothing but an address. Now look at the address. What is the address here? Okay, what is the address here? So again, D2 is the opcode for jump no carry instruction. JNC instruction has an opcode of D2. And again, for every instruction that you write, it has an opcode. It comes with an opcode, right? And what is this? 805D, again, consider the little endian byte ordering. And in little endian byte ordering, what is this? 805D. But what is 805D? Look very carefully here. The addresses where we have stored everything. What is 805D? 805D is the address where the label occurs. So where is the label appears? Where does the label appear? The label appears at memory location 805D. So I asked the jump instruction to make sure to move the program counter to this particular label. Now what is the particular label? This is nothing but the memory address. What is the memory address? 805D. Okay, so this jump instruction comes appended with the address where I want the jump to take the program counter. Okay, now so this was the instruction that we were going to execute, jump instruction. Now conditional jump instruction. Now look carefully, how many machine cycles would a conditional jump instruction have? How many machine cycles would a conditional jump instruction have? Okay, a conditional jump instruction has a variable number of machine cycles. A conditional jump instruction has a variable number of machine cycles. So this is very important for you to understand very clearly. A conditional jump instruction has a variable number of machine cycles. Here, the conditional jump instruction is shown to have 3 machine cycles, namely 1 opcode fetch to fetch the opcode and 2 memory reads to read the memory address. Okay? 1 opcode fetch, 4 clock cycles, and 2 memory reads, 3 clock cycles each. So 10 clock cycles in total. Okay, so 10 clock cycles in total, and it has 3 machine cycles. Okay, but that will be it if the condition is false. But if the condition is true, it executes 1 more machine cycle. Okay, it takes 1 more machine cycle. Okay, and we shall discuss these things, that conditional jumps and conditional call instructions, they have variable number of t states and variable number of machine cycles based on whether the condition is true or false. If the condition is true, it takes up variable certain number of machine cycles, and when if the condition is true, false, then it takes up a certain number of machine cycles. So this is the number of machine cycles it's going to take if the condition is false. Okay, and now the carry flag has not been set. Since the carry flag has not been set, okay, what will happen? The program counter will proceed as expected. What is the program counter's value currently? The program counter's value is 8059. So execute the jump instruction. Let's execute the jump instruction. So jump instruction has been executed. Okay, jump instruction has been executed, and what is the value of the program counter now? The value of the program counter is 805D, right? So 805D is the value of the program counter. Okay, so look very carefully what happened in this jump no carry instruction. The instruction saw that there was no carry, right? So it will set the program counter to this label's value. What is the value of this label? The value of this label is this particular address. So the program counter has now been set to 805D. So next time I hit next, what will happen? The instruction that is pointed by this program counter will be executed, right? The instruction that is pointed by this instruction, this value of the program counter will be executed. So if I look very carefully here, if I go forward, what happened? This instruction was skipped over. Why was this instruction skipped over? Because this jump instruction was responsible for setting the value of the program counter. So the jump instruction was responsible for setting the value of the program counter. Okay, so the program counter was set to 805D, and accordingly, what happened? The jump instruction took the program counter to 805D, and when I hit next, this instruction was skipped. So C was not incremented. Okay, so C was 0 and it remained 0, right? So if I move forward, so this happens like the previous one, and the result is stored in memory location 3458, right? Done. So there was no carry. I did not talk about the carry either. But what if there is a carry? What if there is a carry? Say maybe this is AB. Okay, this is AB. So one of the numbers is 78, the other is AB. Let's assemble the program. So go step by step, move forward. Right? So now my accumulator has 78, my register B has AB. I'm adding these two numbers. Of course, after doing the addition, the sum will be stored in the accumulator, and there will definitely be a carry because the sum is going to be larger than FF, and the carry flag will reflect that. So now, of course, I have done the addition, right? Addition has been done. So the sum is 2, 3. But what is the carry? There is a carry, right? There is indeed a carry. So the carry flag has been set. The carry flag has been set. Now, if I do execute the next instruction, which is jump no carry, what happens? I have now executed this instruction. So now this instruction is looking at the carry flag. If the carry flag, so now the carry flag has been set. So now this instruction is looking at a false condition, right? This is looking whether the carry flag has not been set, but the carry flag has been set. So this instruction has seen a false condition, right? So carry flag has not been set. So the carry flag has been set. And since the carry flag has been set, it will do nothing to the program counter. It will do no modification to the program counter. So the program counter will execute as it should have. Okay. So previously, since in the previous example, the carry flag was not set, and accordingly, this instruction was true. I mean, this condition was true. And since this condition was true, the carry flag, the jump instruction set the program counter to this address, right? Now this instruction, this condition has been false, okay, because the carry flag has been set, this condition has been false, and the jump instruction has done nothing to the program counter. So the program counter has a value of 805C. What is 805C? It is just the next instruction, which is the INR instruction, right? So now if I increment this, what happens? The register C has been now incremented. So now it has a value of 1. Now if I go on and store everything, what I have now? Now I have the sum stored in memory 3458 and the carry stored in memory 3459, right? So that has been done through the jump instruction. So let me again explain this with a very simple example here. Demonstrate this by writing everything here. So I am saying jump no carry, and then again I am putting a label. Now this label is nothing but an address, right? This label is nothing but an address. Now this jump instruction in our example here, this jump instruction was occurring at a memory address of 8059. So this was occurring at a memory address of 8059. Okay. Again, it's a 3-byte instruction, right? It's a 3-byte instruction. So what is the next instruction's address? That will be 80. So the next instruction's address is 8059 plus 3. So that's going to be 805C, right? So this was going to be 805C. So this was INR C, right? And then we had the label. But what was the label? The label was the address for the next instruction. So let's instead write this 805D. Okay, so 805D, at memory location 805D, I have the next few instructions. So INX, H, and so on, next few instructions. So now there are two possibilities. So when I am executing this instruction, it checks for the carry flag. So if the carry flag has not been set, then it makes the program counter equal to, then it sets the program counter to this 805D, so that the next instruction that is executed is this one, and it skips over this instruction. This instruction is skipped over. And if the carry flag has been set, then the program counter gets its value as 805C. So the next instruction is this one. So that is how a conditional jump takes place. Okay, so it checks for the condition. If the condition is true, then the program counter is set to the label. If the condition is false, then the program counter is set to the address of the next instruction, right? And that is how a jump instruction would take place, right? Just as a similar example, if I did write something very similar, for example, did something very similar here. Okay, now instead of saying jump no carry and something like this, so say instead of saying that, I said something like jump carry and checked about this 805D, something like that. Again, I'm showing you another example. So this would do check the carry flag, and if the carry flag has been set to 1, then it will set the program counter to this. Then it will, so now the condition would be true if the carry flag has been set, and the condition would be false if the carry flag has not been set, something like that. Okay, again this could be some other address, I don't know, maybe this could be an address of, say for example 80, who knows, maybe 8060, something like that. So in that case 805C would be this, 8060 would be this, something like that. Okay, again let me copy this and again write down something like that here. Again see this, for example, instead of this carry instruction, say maybe I have a JNZ instruction. Okay, JNZ instruction, right? And maybe this is 8095, so far away. So again this is this address again. Now again this is checking whether the zero flag has not been set. If the zero flag has not been set, so if the zero flag has not been set, if Z is equal to 0, then what will it do? If the zero flag is not set, if the zero flag has not been set, then the condition is true, and if the condition is true, then the program counter will be set to jump to this. So the program counter will now become 8095. So all the instructions that came in between these will be skipped over, and this will be executed next. But if the zero flag was set such that the condition was false, okay, zero flag was set and the condition was false in this scenario, if this would happen, then the program counter will be set to the address of the next instruction, which would be 805C, and as such nothing will happen. The program counter will go its merry way, executing the next instruction as follows. So with this we can actually implement if else. Okay, so these instructions, these conditional jump instructions, are executing something like conditional statements like if else. So this is how we can employ conditions into our program, right? So that will be the end of our discussion at this moment. So feel free to ask if you have any query, and I'll be here for 5 more minutes. So if you have any query, feel free to ask. So for conditional jump instructions, or in fact for any jump instruction, its responsibility is to set the value of the program counter. Okay, it sets the value of the program counter. Okay, so if the condition is true, the value of the program counter is set to the address of the jumps label. Okay, and if the condition is false, then the value of the program counter is set to the address of the next instruction, and that is true for all the jumps. So with that said, feel free to ask if you have any query. So we have reached the end of our discussion. Again, we shall continue this discussion onto the next class. So we shall see all of the jump instructions in action. So in a sense, again, feel free to ask any question that you might have. Okay. So in a sense, this is how conditional jumps really work. So the instruction is some conditional jump to a certain label. So label is nothing but an address, right? Okay, so with that said, if the condition is true, then program counter is set to the address of label. Okay, so that the next instruction that is executed is the instruction which appears with the label, right? And if the condition is false, then the value of the program counter is set to the address of the next instruction. And by next instruction, I mean the instruction that appears right next to the jump instruction itself. Okay, by next instruction, I mean the instruction that appears right next to the jump instruction. So that is how a conditional jump really works. And again, any conditional jump takes up 3 clock cycles if the condition is false. 3 machine cycles. Okay, 3 machine cycles if the condition is false, and 4 machine cycles if the condition is true. And there is a reason for that. Okay, so 3 machine cycles, and if the condition is true, then 4 machine cycles, and if the condition is false, then 3 machine cycles. Okay, of course the 3 is true, I mean 3 machine cycles, that's true always, and 1 additional machine cycle if the condition is true. Okay, so that's what you have to remember in this particular scenario. Okay, we shall discuss this later on. So all the conditional jumps have variable number of machine cycles. So feel free to ask any question that you might have as today's discussion went. So far, if you go back, so we have talked about the flag register in details. Okay, what are the separate flags? We talked about negative numbers in binary. Okay, how negative numbers are treated by means of 2's complement. Okay, 2's complement of the binary numbers, and we discussed that in complete details, and we discussed the fact that the microprocessor really knows nothing about negative numbers, right? It's up to us as the programmers to deal with those. Okay, and we saw examples of such, and we saw and then we saw all the jump instructions, all the different jump instructions, and which conditions are considered true and which conditions are considered false for the particular jump instructions. So these are the entire list of jump instructions, and we saw examples. Okay, and we saw some we shall see some more concrete examples later on in the next class. And in any case, if you have any query, feel free to ask, and if you don't have any more queries, please let me know that you actually understood anything from today's class. And again, I would encourage strongly to install Java runtime in your computer, and install Java runtime in your computer, and run this programmer here, so that actually you get to do these things by yourself. Okay, and this is a very good software, as again I told you, because it lets you see everything about the instructions and all, right? For example, I'm showing you LXI instruction. LXI instruction has one memory read, one opcode fetch, 2 memory reads, and you can see everything that is happening inside that instruction. So everything is shown in a step-by-step fashion in this. So yes, again, feel free to ask if you have any query. Otherwise, we would end our discussion right now here. All right. Again, we shall continue this class on the next one. Again, don't worry, we shall see a few concrete examples later on. And you are having your laboratory experiments as well. There you are seeing some more concrete examples again. Here in this theory class, our goal is to clear up the theoretical ideas, right? Again, feel free to ask if you have any query, or otherwise confirm that you have understood everything or at least something. All right, since it seems like you people don't have any doubt, or maybe you don't want to say anything, all right, so we are going to end our discussion here. All right, so thank you very much for being here for the last like 2 hours 20 minutes. It's been a long class, long day, and we had some internet issues right on the onset. And okay, so we shall continue our discussion on the next class. So thank you very much for being here. And just a reminder that our next class is probably going to be on Saturday on this microprocessor, because I have other engagement, other classes throughout the rest of the week. And so just keep in mind what we discussed today, because we shall continue from where we are leaving off today. Okay, so with that said, thank you very much for being here, and I shall see you on Saturday. Thank you.